Hello, my name is Alen Turnwald, and this video is about using Matlab and Simulink in control engineering. Specifically, it's about designing and testing controllers for the so-called Pendulum-Cart System, for which an example is a circuit robot developed by the students at the University of Kaiserslautern. The model of the system has two coordinates, which are q1 the displacement of the cart and q2 the angle of the pendulum. Using the Lagrange formalism or the Newton-Euler method, you will end up with the differential equations in this form, which are the equations of motion of the system. You can define the state vector x as q and q dot, which are these two again, and the velocities, corresponding velocities, and at the end, using the Taylor method, you can linearize these nonlinear equations around the zero, around the origin, basically, to get the linear differential equation or the system equation in the state space representation. Here we only handle linear systems, design linear controllers. Nevertheless, I have uploaded the nonlinear model of the system, including an animation for testing the controllers afterwards. So once you download this zip file and extract it, you will see the Matlab, the Simulink model of the system. You can open. There is a function called plot which you don't actually use as it is. It's only called by the Simulink model for the animation. Once you click on the run, it should basically start running after a while of compiling, and you will see the animation of the system. There is a trajectory planned to let the cart move from 1.5 meters to -1.5 meters, and the angle of the pendulum should be for all time 0. So this is basically what we are going to generate at the end of this video. Once you click on stop, also the curves of Q1 and Q2 appear. So we start with a new script. Save it first. Call it, let's say, my task or something, and start writing down our code. So we begin our script with a CLC clear and a close to clear everything, and then start entering all of these parameters given as here, and just type everything down. And now insert or define your matrices A and B to define the system completely in Matlab. As you can see, since the parameters are defined as numbers, you can just go ahead and use the parameters in your matrices. Of course, your system needs an output. For example, for taking Q2 as the output of the system, you define the C matrix like this, the second basically component of the state vector. And you could of course define C to be 1 0 0 0 to take the Q1 as the output of the system. For completing the system, of course, you're going to need a D. And now basically you can build the system. For that, of course, we need the command state space, or SS. Let's call this sys. It's a system of A, B, C, and D. And once you let me bring this over here. So now your system is defined in the state space representation, and A, B, C, and D matrices are given here. Next, we are going to do a short analysis of the system. For example, is the system stable or not? You can use eigen, which gives you the eigenvalues of A, and find out the poles of the system. The command pole gives you the same result. You say that there's at least one pole on the right hand side of the S-plane, which means that the system is not stable. You can also use CTRB. Let's use this to decide to find the controllability matrix, and the observability matrix is given by OBSV of the sys, and you see that these are the two matrices. If the rank of these two matrices is 4, which is the system order, the system is respectively controllable and observable. You can already see here that the system is not observable, but it's probably controllable. So you can take a look at the rank of SC, which is 4, and the rank of SO is 3. So the reason is we have actually chosen, let's say, the wrong output. So having Q2 as the output makes the system not observable, but doing the same, choosing Q1 as the output, makes the observability matrix of the system also full rank. So you see that rank of SO is also 4. Let's also take a look at the root locus curve of the system, and you see that the poles of the system are one of them at least always here on the right hand side. This means that there's no P controller that can stabilize the system. There's no gain that brings all of the poles on the left hand side. This means that the P controller is not enough for the system. So we need a dynamical system, or in this case we are going to have a state feedback controller. But before designing the controller, let's simulate the behavior of the system using Simulink, where we start with a new model. Let's call my model and open it. Once you have your Simulink model, let me close this figure. Once you have the Simulink model, you can use the libraries of Simulink, or the newest versions of Simulink allow you to just double click and type stuff. So for simulating a dynamical system or a differential equation like this, you basically need an integrator to integrate x to come to x dot to come to x. So what we need is an integrator. Of course, an integrator needs an initial condition. Let's call this x0 and define it later in the script. So basically we are building this differential equation. It says here's x dot and here's x, which means that we need to build x dot as a sum of these two terms. So what we definitely need is a sum. So we are here building the x dot. X dot is the sum of two terms. One of them is a times x and the other one is b times u. So this times is a times x, this multiplication. For that we use a gain, for example, because it's a constant multiplication. This is the b, and that one is a. Of course, you need to be careful that this is a matrix multiplication and not an element-wise multiplication, both of them. So now a needs the x, which is already here. So this means that this is our input, this is our u, and of course we need the output too. You can copy this gain and connect it to the x. So this is our output, this is our input. Now we have built the system, but let's go one step further and put that all together in a subsystem. You can just select that area and click on create subsystem. Now you have generated your system in a subsystem. If you enter that, you will see here inputs and output ports. Let's give them names like as they are in our differential equation, u and y. Of course, you also need your state vector x coming out of the subsystem. So now we have y, x, and the input u. For simulating, let's start with a constant 0 input, and so we right now don't need the output, and want to take a look at the input. So let's go. So right now you are able to run your simulation and see what happens. There's an error. It says x0, which was the initial condition of this integrator, is not defined. This is why. This is because you haven't defined your initial condition yet. So let's. We don't need that anymore. Let's define our initial condition to be, for example, 0 for the position of the cart. Let's say 5 degrees for the angle, and 0 for the velocity, and 0 for the angular velocity. So once you have run this script, now x0 is also defined in your workspace, and now the simulation has been running, and as we desired, because of the system is not stable, every state goes to infinity. Now let's design a state feedback controller. That, for example, shifts the poles of the system all to -3. So your desired poles are all at -3, and your controller is then given by the command ACR, A, B, and desired poles. Of course, you can also use the command place. You can take a look into the documentation to see what the differences are between these two commands. But once you run your script, let me remove the semicolon here to see the value of k. Once you run your script, you see that k is calculated by the command ACR. And now you can basically feedback your state here to there. For that, you can even copy the gain you have been using here, call it k. Of course, it should be a negative feedback, that is -k. Let's remove this one here, and you see now once you run your controller, the system is stabilized. We can even take a look at the different behavior of the system for different parameters of the controller. For example, if the poles are all at 1.5, what happens to the state? You see that the controller is slower, and if you make it faster, the controller becomes faster. Well, you can even go way further to the left with the poles, and you see that it's actually pretty good what this behavior of the states looks like. But there is a problem, which is the input. Let's now take a look also at the input generated with the controller, which is basically our input of word to create this behavior. Now if you click here, you will see that your controller is using something like -10,000 newtons basically to generate this behavior. And once you have like 0.5, you'll see that the input effort is much less. So obviously there's a trade-off between input effort and the performance of the controller in the closed loop. And one way is to test and check what the behavior of the closed loop at the end is, or you can, instead of using ACAR, also use the LQR the command LQR to design an optimal controller using the linear quadratic regulation or regulator controller. And of course for that you need a Q and R, which you can see into the documentation of the command LQR to see how Q and R are defined. But let's go with I of 4 for Q and R is 1. So now the controller's designed, and we change the controller to the KLQR. You see that the behavior is almost similar, but now if you go lower with R, the input becomes less important. This means that the input effort becomes a bit larger, and on the other side the behavior of the closed loop is better. And now we can go, for example, 5 times unity matrix. You see that the behavior is still getting better, the performance is getting better. So this is another way of designing the controller for the system. Well, something I want to add here is a desired trajectory. For example, for the position of the card to not only be 0 but something else, that a position that we desire. For that, let's also put our controller into a subsystem. Let's call it the controller. Here you have your output is basically you, and your you could actually rotate that and make it look like this. Your input is X. Of course, you can take another input, which is, for example, the desired position of the card. Now you have to add that negatively to the state vector. But of course you cannot add this number to the whole of the components of the state vector. So obviously you need to make the dimensions match. So you have a vector like this to make this guy also a vector of 4 by 1. So now you see you have another input here. For example, if you have a constant of 1, that tells your controller that the position of the card should go to 1. And you see this is actually what is happening. But as you already know, in the practice there are no time or continuous time controllers. You basically implement your controller on a digital computer, on a digital system. So it means that you have to actually implement a time or discrete time controller. So how do we do this? Basically we have a system which is in time continuous time domain, and we have to basically discretize that. For example, you can use it by a 0 order hold, and give it a sample time. You can use the same block for sampling the states of the system, and also the same. Of course, you have to define this time, and first of all, you need to discretize your system, and then have a time discrete time controller. So first of all, we use the command C to D, and let's say sys D equals to C to D of our system with TS. First of all, we need to define TS. Let's go with 100 milliseconds. Of course, we need to bring this back again. And, okay, now we have a discrete time state space representation of a system with a sample time of TS, and so let's call a D equals to sysDA, so we get the matrices of the time discrete system. So of course we need B, C, and D. And basically what we do is just use the same method, for example pole shifting or LQR or whatever, to design now the controller for the time discrete or discrete time system. You know that discrete time system is stable once the poles are all within the unity circle. So we'll place, for example, the poles, all of them here. We call this the KD, which is the discrete time controller. Of course, we have to get these, and now we design the controller. So now let's mark this place, which is, this is where we have a time discrete system, and this is our continuous time world. Okay, we can even change this color, for example the aerial color to, let's say, yellow or whatever. So this is the discrete time world, this is the continuous time world. So we have still our trajectory, but the controller is now the time discrete controller. So the last thing I'm going to talk about is now the state observer. So obviously it's a good controller if you have access to all of the states of the system, but it's in the practice not always the case. So this means that you somehow need to reconstruct the states, because actually what you have is the output of the system and not the state. So what you do is basically you bring out the output where you have installed your sensors, and the state is actually inside the system but not visible for you. So how do we now from here, from the output, reconstruct the states of the system to fit it into the controller to create the same behavior? So a state observer is basically a reproduction of the system, which means you just take your system and reproduce it here as a model. Of course, we are designing a discrete time observer. This means that you can actually copy that right here and call it the observer, which has, of course, the input. So which means you have to feed your input to that observer. You have of course the output of the observer, which you don't need, and the state of that observer is basically the estimation or the reconstruction of the states of the system. So as you see, the observer runs parallel to the system and reconstructs out of the input and somehow the output of the system the states. So what is inside it is, first of all, not an integrator. It's basically a time delay. So which is basically it says that we are using a discrete time system. As the initial condition, we always have 0 because we don't actually know where the initial conditions of the system is. You have here CD, AD, and BD. So we are basically, we don't right now need to bring out the output of the system. So we see that we are now reconstructing the input to state behavior of the system. But what you also need is somehow the output of the real system. So we also bring in Y. So what we do now is comparing the output of our model, of our observer, with the output of the system itself. So we just add a summation. That one is negative, and the output of the model is positive. And so you bring that back with a so-called observer gain. Let's call it K observer, or just OB, like the observer. Force also negative. Now we add this also to here. So now let's rearrange these guys here. That and this. Now this observer is producing the state vector of the system. Let's now take a look at the behavior of the observer. We still feed back this real state vector of the system and just take a look at the states of the observer. Well, observer design is basically a dual problem to controller design. So what you do is you design the observer first using CD and A transpose, and it should basically be faster than the controller. Yeah, sure. Should be now. Okay, now the observer is designed, and if everything is okay, you see that this is a reproduction of the state vector, which is almost quite accurate. You see, and now what we can do is we forget about the states of the system, and we just take the states reconstructed or estimated by the observer to feed back and close the control loop. And you see that well, everything is actually working pretty good. As a very last step, we are going to verify our controller on the real system, which is the nonlinear model I have uploaded. For that, we just replace the controller by the plant from the model online. Of course, you have to note that you have the state vector coming out here. You need to generate your output, so for that you just need to for example, copy this gain C, and then you have already your output. Just delete this, and yeah, I will replace the trajectory also by a trajectory that is basically an alternating value between 1.5 and -1.5 multiplied by a step with a step time of 5 that starts at 5 seconds. And change the values here to x0. This is the mask of the model, and I'm going to change the controller. Instead of pole placement, I use it OQR controller, and run the script again. Now if you run the script here, you'll see that everything is working, and the trajectory, basically the point you have assigned is reached. So you can do the simulation a bit longer. The very beginning, it stabilizes the system, and then the robot is starting moving from 1.5 to -1.5. So that's it. I hope you enjoyed this video and you're able to redo all of these steps. If you have any questions, you can just write me, or if you are at the university, just come to my office and ask your questions.